Every simulation you have ever seen, every weather forecast rendered on a screen, every nuclear explosion modeled inside a supercomputer, every protein folded by an algorithm was produced by a machine whose logic you could, in principle, trace step by step. Classical computers are transparent. You can open the box and follow the math. But right now, in laboratories scattered across the world, machines are being assembled whose internal operations will soon become permanently impossible to simulate, verify, or even comprehend using any classical system that exists or could ever exist. Not because we lack funding, not because we lack cleverness, but because the mathematics forbids it. We are approaching a boundary not of engineering but of knowability. A threshold beyond which humanity will operate tools whose workings exceed our ability to model them, even if we converted the entire observable universe into a single classical computer. This is not speculation. The math is settled. The engineering is catching up. And once we cross that line, there is no return. This is the story of that line. Let us start with something you probably take for granted. Prediction. You check the weather before you leave the house. You trust that the traffic app on your phone knows which highway is jammed. You assume that the bridge you are driving over was stress tested by a computer model before it was built. And you are right to trust these things. Because behind every forecast, behind every simulation, behind every model of a wing or a drug molecule or a crashing car, there is a classical computer doing what classical computers do best. It is taking numbers, feeding them through equations, and spitting out results one step at a time. This process is the invisible backbone of modern civilization. It is so reliable, so omnipresent, so deeply woven into the machinery of daily life that we have forgotten something important about it. We have forgotten that it works only because the systems it simulates are, in a very specific mathematical sense, simple. That word might surprise you. A global weather model tracking millions of data points across the atmosphere does not feel simple. A simulation of a supernova consuming a star does not feel simple. But from the perspective of computational complexity, these systems share a common trait. They obey rules that scale in a way a classical machine can handle. You add more atmosphere, you need more computing power, but the relationship is manageable. Double the grid resolution, and you might need 8 times the processing power. That is a cubic scaling. It is steep, but it is polynomial. And polynomial scaling is the playing field where classical computers are kings. Give them enough time, enough memory, enough transistors, and they will grind through any polynomial problem eventually. This is the domain of predictability. This is the world you live in when the simulation on the screen matches the crash on the test track, when the protein folds the way the algorithm said it would. It is the world where our models reach out and touch reality and the handshake is firm. But there is another domain, a domain where the handshake fails, where our best computers reach out and grasp nothing but smoke. And this domain is not hiding in some exotic corner of theoretical physics. It is sitting inside every atom of your body. It is quantum mechanics. To understand why quantum systems break classical simulation, we need to look at the simplest possible quantum object, a single quantum bit, a qubit. In a classical computer, a bit is either 0 or 1. It is a switch. It is on or it is off. There is no ambiguity. You can write its state with a single number, but a qubit is different. A qubit can be 0, it can be 1, or it can be in a superposition of both simultaneously. To describe this superposition, you do not need one number, you need two. Two complex numbers called probability amplitudes. One tells you how much of the qubit is leaning toward 0, the other tells you how much is leaning toward 1. Together, they define the complete quantum state of that single qubit. Two numbers. That does not sound like a problem. Any pocket calculator can handle 2 numbers. Now add a second qubit. If these 2 qubits are entangled, which is to say they are correlated in that peculiarly quantum way where the state of one depends on the state of the other, you cannot describe them separately. You cannot just say, the first qubit has these 2 numbers, and the second qubit has those 2 numbers. The entanglement means the system must be described as a whole. And to describe the whole, you need 4 complex numbers, one for each of the 4 possible combined states. Both 0. First 0, second 1. First 1, second 0. Both 1. 4 numbers, still easy. Add a third qubit. Now you need 8 numbers, 4 qubits. 16 numbers, 5 qubits. 32 numbers. You see the pattern. Every single qubit you add to the system doubles the number of complex numbers a classical machine must track. This is not polynomial growth. This is exponential growth. And exponential growth is the monster that eats civilizations. Let us put numbers to this. 10 qubits require 1,024 complex numbers. 20 qubits require roughly 1 million. 30 qubits require about 1 billion. At 40 qubits, you are looking at roughly 1 trillion complex numbers. Each of those numbers is a complex number, meaning it has 2 components, a real part and an imaginary part. So the raw data a classical computer needs to store in its memory to represent a 40-qubit quantum system is on the order of 16 terabytes. That is within reach of a high-end server. Difficult, but possible. At 50 qubits, the numbers explode. 2 to the power of 50 is roughly 1 quadrillion. The memory required to store the full quantum state exceeds what any single machine on Earth possesses. Supercomputers can manage it, barely, by distributing the computation across thousands of nodes, but we are already sweating. Now go to 100 qubits. 2 to the power of 100 is a number so large that writing it out would take 31 digits. It is roughly 1.27 followed by 30 zeros. To store that many complex numbers, you would need more memory than exists in all the computers on the planet combined. Every server farm, every data center, every laptop and phone and smartwatch on Earth, pooled together, could not hold the quantum state of 100 entangled qubits. And we are just getting started. At 300 qubits, the number of complex amplitudes exceeds the estimated number of atoms in the observable universe. That number is roughly 10 to the power of 80. 2 to the power of 300 is approximately 10 to the power of 90. You would need more storage units than there are particles in the cosmos. Not megabytes, not hard drives, atoms. You would need more atoms to store the data than exist in reality. At this point, the problem is not about building a bigger computer. It is about the physical limits of the universe itself. The universe does not contain enough matter to classically represent the quantum state of 300 entangled qubits. This is the wall. And it is important to understand that this wall is not made of engineering limitations. It is not like the sound barrier, which we broke with better engines. It is not like the speed of light, which is a physical constant we might someday work around with exotic physics. This wall is mathematical. It is a consequence of the exponential structure of quantum mechanics. It does not care about Moore's law. It does not care about breakthroughs in chip fabrication. It does not care about artificial intelligence optimizing classical algorithms. You could wait 1,000 years for classical technology to improve, and the wall would still be standing, because the wall grows faster than any polynomial technology can climb. Let us give this wall a proper name. It is called Hilbert space. Hilbert space is the mathematical arena where quantum states live. For a system of n qubits, the Hilbert space has 2 to the power of n dimensions. Each dimension represents a possible configuration of the system. A classical computer trying to simulate this system must navigate that Hilbert space by tracking a vector, an arrow, pointing in some direction within those exponentially many dimensions. Every quantum operation, every gate applied to the qubits rotates that arrow. The simulation amounts to performing matrix multiplications on vectors in a space whose dimensionality doubles with every new qubit. To make this tangible, imagine you are trying to describe the position of a ball on a table. The table is flat, two-dimensional. You need two numbers, an x-coordinate and a y-coordinate. Now imagine the ball is moving through a room, 3 dimensions. You need 3 numbers. Now imagine the ball is moving through a space with 4 dimensions. You cannot picture it, but the math still works. You need 4 numbers. A qubit system with 50 qubits lives in a space with over 1 quadrillion dimensions. A system with 300 qubits lives in a space with more dimensions than there are atoms in existence. Your ball is moving through a room so vast that the room itself cannot fit inside the physical universe. This is not an abstraction. This is what nature is doing every time 2 particles interact. Every time a photon bounces off your skin. Every time an electron shifts its orbit inside an atom. Nature is navigating a Hilbert space of incomprehensible dimensionality, and it is doing so effortlessly, instantly, without breaking a sweat. The universe does not need to store those amplitudes in memory. It does not need to perform matrix multiplications on a chip. The quantum system simply is the computation. The physics is the math. They are the same thing. And this is the crack in the wall. Because when we build a quantum computer, we are not building a device that simulates quantum mechanics. We are building a device that is quantum mechanics. We are harnessing the very fabric of reality to do computation in a space that no classical machine can enter. The quantum computer does not fight the exponential scaling, it lives inside it. But before we get ahead of ourselves, we need to address the obvious objection. You might be thinking, sure, the full quantum state is enormous, but do we really need to track all of it? Maybe there are shortcuts. Maybe we can approximate. And you would be right to think this. Classical physicists are not fools. They have developed brilliant techniques to simulate quantum systems without tracking every single amplitude. These techniques have names like density matrix renormalization group, tensor network methods, and Monte Carlo sampling. They exploit the fact that many real quantum systems do not actually explore the full Hilbert space. They tend to stay in a corner of it, a low entanglement region where the state can be described more efficiently. For example, the ground state of a one-dimensional chain of atoms can often be captured by a mathematical object called a matrix product state, which requires memory that grows only linearly with the number of atoms rather than exponentially. These methods have been spectacularly successful. They have allowed classical computers to simulate quantum materials, calculate the energy levels of molecules, and even challenge early claims of quantum supremacy. But here is the critical point. These shortcuts work precisely because the systems they simulate have limited entanglement. The moment entanglement grows, the moment the quantum state spreads its correlations across many qubits in a complex, non-local pattern, the shortcuts collapse. The tensor networks become too wide. The matrix product states require exponentially growing bond dimensions. The Monte Carlo methods hit what is called the sign problem, where positive and negative contributions cancel each other out, and the statistical noise drowns the signal. The sign problem, in particular, is not just a nuisance. For a wide class of quantum systems, including many that are physically important, such as strongly correlated electron systems and certain lattice gauge theories, the sign problem is provably hard. It is believed to be computationally intractable for classical machines. No known classical algorithm can efficiently solve it in the general case. This means that the clever tricks work only in a limited regime. They are flashlights in a dark room. They illuminate the corners, the edges, the nearby furniture. But the room itself, the full Hilbert space, remains vast and dark. The current frontier of classical simulation sits at roughly 40 to 60 qubits for exact state vector simulation, depending on the available supercomputing resources. In 2019, when Google ran their Sycamore experiment with 53 qubits, they chose a circuit specifically designed to generate enough entanglement to push beyond this frontier. IBM pushed back, arguing that with enough disk storage and clever algorithms, a classical supercomputer could complete the task in days rather than millennia. And they were partially right. The boundary is not sharp, it is contested. Classical researchers keep finding new tricks, and the goalpost keeps moving. But the goalpost can only move so far. Because the exponential wall does not move, it is the classical tricks that are running out of room. Think of it this way. Imagine you are trying to climb a mountain that doubles in height every time you take a step. Your climbing gear improves by 10% each year. In the early going, your improving gear keeps pace. The first few doublings are manageable, but eventually, inevitably, the mountain outgrows your equipment, not because your gear is bad, but because no linear or polynomial improvement can keep up with exponential growth. This is the fundamental asymmetry between classical and quantum computation. Classical resources are bounded by polynomial growth. Quantum state space grows exponentially. The two curves must eventually diverge, and once they do, the gap becomes uncrossable. There is something almost eerie about this asymmetry when you stop to think about it. Nature runs quantum mechanics on everything. Every atom in your body is a quantum system. Every photon of light reflecting off your screen is governed by quantum electrodynamics, a theory whose calculations involve the full machinery of quantum field theory and Hilbert spaces of effectively infinite dimension. The chair you are sitting on is a quantum system composed of roughly 10 to the power of 27 atoms, each entangled with its neighbors in a complex web of electromagnetic interactions. Nature handles this effortlessly. The chair does not lag. The chair does not buffer. The chair does not run out of memory. The universe is running the most powerful quantum computation imaginable, and it is doing so on every object in existence simultaneously. But when we try to write down what the universe is doing, when we try to translate the quantum computation into classical language, into numbers on a page or bits in a memory chip, the translation breaks down. The classical description cannot keep up. It is as if the universe is speaking a language with an infinite vocabulary, and our classical computers can only write in an alphabet of 26 letters. For simple sentences, the translation works. For poetry, it struggles. For the full symphony of quantum reality, it fails completely. This is the deepest lesson of quantum computation. It is not that we need faster computers. It is that the language of classical physics is fundamentally insufficient to describe what nature is doing. The exponential wall is not a barrier to be overcome. It is a message. It is the universe telling us that there is more going on inside a handful of atoms than all the classical computers ever built can capture. And the question facing humanity right now is not whether we can make classical computers faster. The question is whether we are willing to stop translating and start speaking the language directly. Because that is what a quantum computer does. It does not simulate quantum mechanics. It speaks quantum mechanics. It operates natively in the Hilbert space that classical machines can only describe from the outside, squinting through a keyhole, catching glimpses of a room they can never enter. The machines being built in laboratories today, the machines with 50, 60, 100 physical qubits, they are standing at the threshold of that room, and the door is opening, not because we pushed it, because we finally built a key that is made of the same material as the lock. The question is no longer whether we can build machines that operate in this space. The question is what happens when we do. What happens when a machine performs a computation that no classical system in the universe can follow? What happens when the output appears on a screen and no human, no algorithm, No supercomputer can trace the steps that produced it. What happens when we build something we cannot simulate? Something we cannot, even in principle, fully understand. The wall of classical simulation is not just a technical obstacle, it is a boundary in the map of human knowledge. And on the other side of that boundary, the territory is unmapped. We have never been there before. No civilization has. No intelligence in the history of the cosmos, as far as we know, has ever built a tool that exceeded the classical description of nature at this scale. We are not just building a faster computer. We are building a window into a part of reality that has always been there, but has never been seen. The Hilbert space of 100 qubits is not a human invention. It is a feature of the universe. It existed before we did. It will exist after we are gone. The atoms in your body navigate it every microsecond. But for the first time in the history of intelligent life, we are building machines that can navigate it deliberately, that can steer through those impossible dimensions and bring back answers. And those answers will come from a place that no classical eye can see. So we have seen the wall. We have seen that the Hilbert space of even a modest quantum system dwarfs the storage capacity of every classical computer on the planet. We have seen that nature speaks a language our machines cannot translate. And the obvious conclusion is breathtaking. If we build a device that operates natively in that Hilbert space, a quantum computer, we gain access to a computational arena that no classical system can enter. The exponential advantage is sitting right there, baked into the mathematics of the universe, waiting to be harvested. But there is a problem, a vicious, stubborn, decades-old problem that nearly killed the entire field before it got started, and that problem is noise. A qubit on paper is a perfect object. It is a mathematical jewel. It holds its superposition with infinite precision. It entangles with its neighbors without a whisper of interference. It rotates through Hilbert space like a frictionless gyroscope, never wobbling, never drifting, never losing its way. On paper, quantum computing is elegant. On paper, it is invincible. In a laboratory, a qubit is a screaming infant in a hurricane. The physical systems we use to build qubits are extraordinarily fragile. Some laboratories use superconducting circuits, tiny loops of metal cooled to temperatures colder than outer space, roughly 15 thousandths of a degree above absolute zero. Others use trapped ions, individual charged atoms suspended in electromagnetic cages and manipulated with laser beams. Others use photons, neutral atoms, nitrogen vacancies in diamond, or the spin states of electrons in silicon. Every one of these platforms shares the same fundamental vulnerability. The quantum state they carry is exquisitely sensitive to disturbance. Imagine trying to balance a pencil on its tip. Not on a table in a quiet room, on the dashboard of a truck driving over a dirt road during an earthquake. That is what maintaining a qubit superposition feels like in a real laboratory. The pencil wants to fall. The universe wants to knock it over. And the universe has an infinite number of ways to do it. A stray photon from the laboratory lights, a vibration from a passing truck outside the building, a fluctuation in the magnetic field from the wiring in the walls, a cosmic ray, a subatomic particle from a supernova that exploded millions of years ago, streaking through the ceiling and slamming into the chip. Each of these disturbances is a tap on the pencil. And in the quantum world, it does not take much of a tap to ruin everything. This process has a name. It is called decoherence. And it is the single greatest enemy of quantum computation. Decoherence is what happens when a qubit's quantum information leaks into the surrounding environment. The qubit does not explode. It does not disappear. It simply becomes entangled with the random noise around it. Its carefully prepared superposition, that delicate balance between 0 and 1, bleeds into the thermal vibrations of the metal, the stray electromagnetic fields, the jostling of nearby atoms. The information is not destroyed, it is scattered. It is diluted into a bath of trillions of particles where it becomes, for all practical purposes, irretrievable. The timescale on which this happens is horrifyingly short. For superconducting qubits, the coherence time, the window during which the qubit maintains its quantum state, is typically measured in microseconds. Some of the best systems in the world achieve coherence times approaching or exceeding 100 microseconds. That sounds like almost nothing, and it is almost nothing. A quantum computation must be set up, executed, and read out within that window, or the information dissolves into noise. This is why the first few decades of quantum computing were an exercise in frustration. Physicists could build qubits, they could perform simple operations, they could demonstrate superposition and entanglement in systems of 2, 3, 5, 10 qubits. But every time they tried to scale up, every time they tried to add more qubits and perform longer computations, the noise won. The errors accumulated faster than the computation could proceed. It was like trying to write a novel on a typewriter where every 10th keystroke randomly changes a letter. For a sentence or two, you can tolerate it. For a paragraph, you can maybe correct by hand. For a full novel, the errors overwhelm the text. You end up with gibberish. This era of quantum computing, the era we have been living through for roughly the past decade, has a name. It is called the Noisy Intermediate Scale Quantum Era, or NISQ. The term was coined by physicist John Preskill in 2018. NISQ devices are machines with tens to a few hundred physical qubits, all of them noisy, all of them error-prone, none of them corrected. They can perform short computations. They can demonstrate quantum effects. They can produce results that are interesting and sometimes impressive, but they operate on a tightrope. Every gate, every operation applied to the qubits introduces a small probability of error. For current hardware, that error rate is typically around 1 in 1,000 for single qubit gates, and roughly 1 in 100 for 2 qubit gates. These sound like small numbers, but in a computation involving thousands or millions of gates, those small probabilities cascade, the errors compound, the signal drowns in static. This is why many of the headline-grabbing quantum experiments of the past several years have been met with skepticism. When Google announced in 2019 that their Sycamore processor had achieved quantum supremacy, the task they demonstrated was a specific sampling problem, a computation carefully chosen to be short enough to complete before decoherence destroyed the state. The circuit was shallow, the computation was fast, and even then, the output was noisy. The result was not a clean answer to a useful question. It was a statistical distribution that matched quantum mechanical predictions better than a classical computer could efficiently reproduce. It was a proof of concept, not a revolution. The NISQ era produced valuable science. It taught engineers how to fabricate qubits, how to wire them together, how to control them with microwave pulses and laser beams. It revealed the engineering challenges of scaling quantum hardware, from the nightmare of wiring hundreds of control lines into a cryogenic refrigerator to the challenge of calibrating qubits that drift out of tune like instruments in an orchestra exposed to changing temperature. But NISQ devices, for all their ingenuity, remained within a contested zone. The computations they performed were either too noisy to be trusted or too simple to be classically intractable. They poked at the boundary of classical simulation without decisively crossing it. They were proof that quantum computing was possible. They were not proof that it was unstoppable. What changes everything? What transforms quantum computing from a laboratory curiosity into an existential event is the idea that noise can be defeated, not reduced, not managed, defeated, systematically, permanently, and at scale. This idea is called quantum error correction, and it is one of the most profound inventions in the history of computation. In classical computing, error correction is straightforward. If you want to protect a bit, you copy it. Store 3 copies instead of 1. You take a majority vote and recover the original. This works because classical bits can be measured and copied freely. Reading a classical bit does not change it. Copying a classical bit is trivial. But in quantum computing, both of these operations are forbidden. You cannot copy a qubit. This is a fundamental law of quantum mechanics called the no-cloning theorem. It states that there is no physical process that can take an arbitrary, unknown quantum state and produce a perfect duplicate. If you try to measure the qubit to find out what it contains, the measurement collapses the superposition. The very act of looking at the qubit destroys the information you are trying to protect. This seems like a death sentence for error correction. How do you fix errors in a system you cannot look at? How do you protect information you cannot copy? The answer, discovered independently by Peter Shaw and Andrew Steen in the mid-1990s, is one of the most ingenious ideas in all of science. You do not copy the qubit. You spread its information across many qubits using entanglement. The information is not stored in any single physical qubit. It is stored in the correlations between qubits. It is distributed, smeared, hidden in the collective state of the group. No individual qubit carries the full message, but the group together holds it perfectly. And here is the key. You can detect errors without ever measuring the protected information. You do this by measuring only the relationships between qubits, not the qubits themselves. These measurements are called syndrome measurements. They tell you whether an error has occurred and where it occurred without revealing anything about the encoded quantum state. It is like detecting that a word has been misspelled in a sealed envelope without ever opening the envelope or learning what the letter says. This is the principle behind quantum error correcting codes. The most widely studied of these codes is called the surface code. In a surface code, one logical qubit, one protected unit of quantum information, is encoded across a grid of many physical qubits. The number depends on the desired level of protection. For a modest level of error suppression, you might encode one logical qubit across 17 physical qubits. For higher protection, you might need hundreds or even thousands. The overhead is enormous. It is the price of reliability. But the payoff is extraordinary, because quantum error-correcting codes have a property called a threshold. If the error rate of each individual physical qubit is below a certain value, the threshold error rate, then adding more physical qubits to the code actually makes the logical qubit more reliable. You read that correctly. Making the system bigger makes it better. This is the opposite of what happens in an uncorrected system, where adding more qubits just adds more noise. Below the threshold, the error-correcting code is winning the fight against decoherence. Every additional layer of redundancy suppresses the logical error rate exponentially. Above the threshold, the noise is too strong and the code cannot keep up. Below it, the code can suppress errors to arbitrarily low levels. You can, in principle, make the logical qubit as perfect as you want, provided you are willing to pay the cost in physical qubits. For the surface code, the threshold error rate is roughly 1% for 2-qubit gates. And this is where the timeline of quantum computing pivots. Because over the last several years, multiple hardware platforms have pushed their physical error rates below this threshold. Superconducting qubits, trapped ions, and neutral atoms have all demonstrated 2-qubit gate error rates in the range of 1/10 to 1/2%. They have crossed the line. They are below the threshold. The era of error correction is no longer theoretical. It is operational. The landmark moment came in December of 2024, when Google's quantum AI team published results from their new processor called Willow. Willow is a superconducting chip with 105 physical qubits. But the significance of Willow was not the qubit count, it was what they demonstrated with those qubits. They built surface codes of increasing size, from a 3 by 3 grid to a 5 by 5 grid to a 7 by 7 grid. And for the first time ever, at this level of scaling, they showed that each increasing code size reduced the logical error rate. The larger code performed better than the smaller code. The error correction was working. The threshold had been crossed, not just in a single isolated measurement, but across a scaling curve. Each step up in code distance cut the logical error rate roughly in half. This is the exponential suppression that theorists had predicted for 30 years. And Willow proved it was real. The importance of this result is difficult to overstate. It is the difference between a technology that gets worse as you scale it and a technology that gets better. It is the difference between a machine that chokes on its own noise and a machine that cleans itself as it grows. It is the difference between niscu and something fundamentally new. Something that can sustain coherent quantum computation not for microseconds, but for as long as the error correction cycle can run. In principle, indefinitely. Google is not alone in this race. In February of 2025, Microsoft announced a breakthrough of a completely different character. Their approach to quantum computing does not use the conventional superconducting qubits or trapped ions. It uses topological qubits, a radically different architecture based on exotic quantum states of matter called Majorana fermions. Topological qubits store information not in the state of a single particle, but in the topology, the geometric structure of a system of particles. This makes them inherently more resistant to local noise. A small disturbance that would destroy a conventional qubit cannot affect a topological one, because the information is encoded in a global property that local perturbations cannot touch. Microsoft's chip, called Majorana One, represents the first quantum processor built on what Microsoft calls a topological core architecture. In a paper published in Nature, the team demonstrated an interferometric readout technique on a novel device made from indium arsenide and aluminum, designed to host exotic quasi-particles called Majorana zero modes. The Nature paper itself was carefully limited in its claims, and the broader scientific community remains divided on whether the device has conclusively demonstrated topological qubits. It is early-stage work, but if the topological approach is validated and scales as its proponents believe it will, it could dramatically reduce the overhead needed for error correction, potentially requiring far fewer physical qubits per logical qubit than the surface code. Meanwhile, IBM has laid out a detailed roadmap toward error-corrected quantum computing, targeting systems with thousands of physical qubits by the middle of this decade, and architectures that combine multiple quantum processors through classical and quantum interconnects. Their approach emphasizes modularity, building quantum systems from linked chips rather than trying to put everything on a single processor. Quantinuum, which uses trapped ion qubits, has demonstrated some of the lowest gate error rates in the industry and has shown that error correction codes perform well in their architecture. Their systems have achieved 2-qubit gate fidelities, exceeding 99.9% across all qubit pairs in a production system, well below the surface code threshold. Each of these efforts represents a different bet on how to reach the same destination. Superconducting circuits are fast but fragile. Trapped ions are precise but slow. Topological qubits are robust in theory but unproven at scale. Neutral atoms, manipulated by optical tweezers, offer a path to large qubit counts with flexible connectivity. The diversity of approaches is itself a signal of the maturity of the field. This is not a single laboratory chasing a dream. This is a global engineering effort converging on a common goal from multiple directions. And that goal is the logical qubit, a qubit that does not decay, a qubit that does not drift, a qubit that holds its quantum state not because the hardware is perfect, but because the software, the error-correcting code, is constantly watching, constantly diagnosing, constantly repairing. There is something almost biological about this process. A living cell is not made of perfect molecules. Its DNA is constantly being damaged by radiation, by chemical reactions, by the simple thermal chaos of being warm and wet. But the cell survives because it has error correction machinery. Enzymes patrol the DNA, detect mismatches, snip out errors, and stitch the strand back together. The cell is reliable not because its components are flawless, but because its repair mechanisms are relentless. A logical qubit works the same way. The physical qubits are noisy. They make errors constantly. But the syndrome measurements detect those errors in real time, and the decoding algorithms correct them before they can corrupt the logical information. The logical qubit is a living thing. It persists not through perfection, but through perpetual self-repair. And this is where we must confront the deeper significance of what is happening. The transition from noisy physical qubits to error-corrected logical qubits is not a gradual improvement. It is not like going from a slow car to a fast car. It is a phase transition. It is like the difference between water and ice. Below the threshold, the system is chaotic. Errors proliferate. Computation dissolves into noise. The machine is useless for any serious purpose. Above the threshold, and here above means the hardware quality is above what the code requires, so the physical error rate is below the threshold value. Order emerges from chaos. The errors are suppressed exponentially. The logical qubit becomes stable. And once it is stable, the exponential scaling of Hilbert space is no longer a theoretical promise. It becomes an operational reality. Consider what this means. A machine with 50 logical qubits, each encoded across perhaps 1,000 physical qubits, would require a total of roughly 50,000 physical qubits. That is within the range of what hardware roadmaps project for the late 2020s or early 2030s. But those 50 logical qubits, protected by error correction, could sustain coherent quantum computation through millions of gate operations. They could explore a Hilbert space of 2 to the power of 50 dimensions, over 1 quadrillion dimensions, with a fidelity that no NISQ device could approach. And the computation would not be a sprint against decoherence. It would be a marathon. The machine could run for as long as the error correction holds, executing deep circuits, performing complex algorithms, reaching into corners of Hilbert space that were previously inaccessible. Scale to a few hundred logical qubits, and the Hilbert space exceeds the descriptive capacity of the observable universe. Scale to 1,000, and you are operating in a mathematical arena so vast that the word large loses all meaning. There is no classical analogy. There is no metaphor big enough. The machine would be manipulating quantum states in a space that makes the number of atoms in the cosmos look like a rounding error. This is why the noise barrier mattered so much. Not because noise is an interesting engineering challenge, but because noise was the only thing standing between us and the abyss. The exponential power of Hilbert space was always there, lurking inside the equations, implicit in the physics. But as long as decoherence destroyed quantum information faster than we could use it, that power was locked away. The noise was the prison gate. Error correction is the key, and it is now turning in the lock. There is an analogy from the history of technology that captures the magnitude of this moment. Before the invention of the vacuum tube and later the transistor, electrical engineers could build simple circuits. They could send telegraph signals. They could amplify sound. But they could not build a general-purpose computer because the components were too unreliable. A computer requires millions of switching operations. And if each switch has even a small chance of failing, the computation collapses. The invention of reliable, scalable switching elements, first tubes, then transistors, then integrated circuits, is what made classical computing possible. It was not the idea of computation that changed. Alan Turing had the idea in 1936. It was the hardware reliability that crossed a threshold. Once the components were good enough, the entire edifice of modern computing followed as an inevitable consequence. We are standing at the equivalent moment for quantum computing. The idea has been here since the 1980s, when Richard Feynman first suggested that quantum systems could be simulated by quantum machines. The algorithms have been here since the 1990s, when Peter Shor showed that a quantum computer could factor large numbers exponentially faster than any known classical method. The theory of error correction has been here for nearly 3 decades. What has been missing is the hardware crossing the threshold, and now, for the first time, it is crossing. The Willow results are not the end of the story. They are the proof of principle. The first transistor in 1947 did not immediately produce a laptop. Decades of engineering, of integration, of miniaturization followed. The same will be true for quantum computing. We are years, probably a decade or more, from machines with thousands of logical qubits running at the scale needed for the most transformative applications. But the trajectory is now clear. The phase transition is happening. The noise barrier, the great filter that kept quantum computing in the realm of theory and demonstration, is being breached. And once it is fully breached, once the logical qubits are stable and plentiful, the exponential engine ignites. The machine will operate in a computational space that no classical system can enter. Not because we choose not to simulate it classically, because we cannot. The wall we described in the beginning is not a challenge to be overcome by the quantum computer. It is a wall that exists only for classical machines. The quantum computer walks through it as if it were not there, because, for quantum mechanics, it never was. The noise was the last defense, the last reason to believe that classical and quantum computation might remain on equal footing. That defense is falling. And when it falls, the landscape on the other side is unlike anything we have encountered in the history of science. Because on the other side, we will be running machines whose internal processes unfold in a space that cannot be written down, cannot be stored, and cannot be classically followed. We will have crossed from the era of machines we can understand into the era of machines we must trust. And that changes the nature of the game entirely, because once the noise is defeated, once the logical qubits are stable and plentiful, the exponential engine ignites. The machine will operate in a computational space that no classical system can enter, not because we choose not to simulate it classically, because we cannot. The wall we described in the beginning is not a challenge to be overcome by the quantum computer. It is a wall that exists only for classical machines. The quantum computer walks through it as if it were not there, because for quantum mechanics, it never was. The noise was the last defense, the last reason to believe that classical and quantum computation might remain on equal footing. That defense is falling. And what lies on the other side is unlike anything we have encountered in the history of science. That question, how do we know the machine is telling the truth, is coming. We will get there, but first, we need to confront something more immediate. Something that has been muddying the water for years. Because if you have followed quantum computing in the news at all, you have been lied to. Not maliciously, not by the physicists themselves, usually, but by the hype machine that surrounds any emerging technology, the press releases, the breathless headlines, the investor presentations with hockey stick graphs, and the word revolution printed in bold. You have been told that quantum computers will break all encryption overnight. You have been told they will cure cancer by simulating every molecule in your body. You have been told they will solve optimization problems that would take classical computers longer than the age of the universe. And some version of some of these claims may eventually turn out to be true. But the way they have been presented has created a fog so thick that even educated people cannot see the actual landscape underneath. So, let us clear the fog. Let us ask the question that matters. What does quantum advantage actually mean? Not in a press release, not in a funding pitch. In the cold, honest language of computational complexity. The story begins in October of 2019, when Google published a paper in Nature that detonated like a bomb in the physics community. Their team had built a processor called Sycamore, a chip with 54 superconducting qubits, of which 53 were operational. They used this processor to perform a very specific task called random circuit sampling. The idea is conceptually straightforward. You apply a sequence of random quantum gates to the qubits, creating a deeply entangled state. Then you measure all the qubits. The output is a string of zeros and ones. You repeat this process many times, collecting millions of output strings. These strings are not uniformly random. Because of the quantum interference in the circuit, some strings are more likely to appear than others. The pattern of which strings appear more or less often is called the output distribution, and that distribution is fiendishly difficult for a classical computer to calculate. Google claimed that Sycamore completed this sampling task in approximately 3 minutes and 20 seconds. They estimated that the most powerful classical supercomputer on Earth, IBM's Summit, would require roughly 10,000 years to perform the same calculation. The ratio is staggering. 3 minutes versus 10,000 years. Google called this quantum supremacy. The word supremacy was chosen deliberately by physicist John Preskill years earlier to describe the moment when a quantum device performs a computation that no classical machine can match in any reasonable time. And for a few weeks, it felt like the threshold had been crossed. The headlines were euphoric. The future had arrived. Then the pushback began. IBM fired the first shot within days. Their researchers argued that Google had dramatically underestimated the power of classical simulation. They pointed out that Summit had enormous amounts of disk storage that could be used as extended memory. By exploiting this storage and using a different simulation strategy, IBM claimed the task could be completed classically in about 2.5 days. Not 10,000 years. 2.5 days. The speedup was still impressive, 3 minutes versus 2.5 days, but it was not the civilizational gulf that the word supremacy implied. Over the following years, classical researchers continued to chip away at the claim. A group in China demonstrated that tensor network methods running on a cluster of graphics processing units could simulate the Sycamore circuit in a matter of hours. Other teams showed that approximate methods, algorithms that do not reproduce the exact output distribution but generate one that is statistically close, could narrow the gap even further. By 2022, several groups had argued that the Sycamore experiment, while impressive, did not represent an unambiguous demonstration of quantum supremacy. The classical goalposts had moved. This pattern, quantum device claims advantage, classical algorithm claws it back, has repeated multiple times since. In 2020, a Chinese team led by Jianwei Pan performed a boson sampling experiment using their photonic quantum computer called Jiuzhang. Boson sampling is a different type of problem from random circuit sampling. Instead of qubits going through gates, it involves sending photons, particles of light, through a network of beam splitters and measuring where they come out. The mathematics of boson sampling is connected to a notoriously difficult mathematical object called the permanent of a matrix, which is believed to be classically intractable to compute exactly. Pan's team reported that Jiuzhang completed in 200 seconds a sampling task that they estimated would take the Sunway Taihu Light supercomputer roughly 2.5 billion years. Again, the claim was extraordinary. And again, classical researchers found ways to narrow the gap, though not as dramatically as with Sycamore. These experiments are important. They represent real milestones, but they also illustrate a deeper truth about quantum advantage that the headlines consistently miss. The tasks being performed, random circuit sampling, boson sampling, are not useful in any practical sense. Nobody needs a random sample from a quantum circuit. Nobody has a business problem that requires the permanent of a large matrix computed to high precision. These are benchmark problems. They are chosen specifically because they are hard for classical computers, not because they solve real-world problems. They are the quantum computing equivalent of a drag race. They prove the engine is powerful. They do not prove the car can navigate a city. This distinction is crucial. There is a spectrum of quantum advantage, and conflating the different points on that spectrum has caused enormous confusion. At one end of the spectrum is quantum speedup. This is the mildest form of advantage. It means a quantum computer can solve a problem faster than a classical computer, but the classical computer can still solve it. The quantum machine is quicker, but the classical machine gets there eventually. This is useful but not revolutionary. A quantum speedup of 2 times or 10 times or even 100 times is nice, but classical hardware improves too. Moore's law, parallelism, better algorithms, these can often close a gap of that size. In the middle of the spectrum is what most people mean when they say quantum supremacy. This is a demonstration that a quantum device can perform a specific task that is practically intractable for any existing classical machine. The key word is practically. It means the classical machine would take an unreasonably long time, years, centuries, millennia, but it could, in principle, do it. Given infinite time and infinite memory, a classical computer could reproduce the result. The task is not impossible for classical machines. It is just absurdly expensive. This is what Google's Sycamore experiment targeted. It is an impressive milestone, but it comes with an asterisk. The asterisk is that classical algorithms are not static. They improve, and every time they improve, they push the boundary of what counts as practically intractable further out. This is why the Sycamore claim eroded over time. The quantum hardware stayed the same. The classical competition got better. At the far end of the spectrum is something much more profound. It is called quantum computational advantage in the complexity theoretic sense. This means that a quantum computer can solve a problem that no classical computer can solve efficiently, not just with existing hardware, but with any classical algorithm running on any classical hardware, now or in the future. This is not about building a bigger supercomputer. This is about proving a mathematical separation between what quantum machines can do and what classical machines can do, regardless of resources. This is where the field of computational complexity enters the picture. And this is where the story gets both more rigorous and more humbling. Computer scientists classify problems into complexity classes based on how the resources required to solve them scale with the size of the input. The most famous class is P, the set of problems that can be solved in polynomial time on a classical computer. These are the easy problems, at least in principle. Then there is no problem, the set of problems whose solutions can be verified in polynomial time, even if finding the solution might be hard. The question of whether P equals no problem, whether every problem whose solution can be quickly checked, can also be quickly solved, is the most famous open question in all of mathematics and computer science. It has remained unsolved since it was formally posed in 1971. Quantum computers have their own complexity class. It is called BQP, which stands for Bounded Error Quantum Polynomial Time. This is the set of problems that a quantum computer can solve in polynomial time with a bounded probability of error. The classical equivalent is BPP, Bounded Error Probabilistic Polynomial Time, the set of problems solvable by a classical computer that can flip coins. The central question of quantum computational advantage is whether BQP is larger than BPP. In plain terms, are there problems that a quantum computer can solve efficiently that no classical computer can? Almost every quantum computing researcher believes the answer is yes. The evidence is overwhelming. Shor's algorithm for factoring large numbers runs in polynomial time on a quantum computer. The best-known classical factoring algorithms run in sub-exponential time, dramatically slower. Grover's algorithm for searching unsorted databases provides a quadratic speedup that is provably optimal. Simulating quantum systems themselves, the very task Feynman envisioned in 1982, appears to be exponentially easier on a quantum machine than on a classical one. But here is the uncomfortable truth that rarely appears in the headlines. It has not been proven. The statement that BQP is strictly larger than BPP is a conjecture. It is one of the most widely believed conjectures in computer science, supported by decades of evidence and the failure of every attempt to find efficient classical algorithms for problems like factoring. But it has not been mathematically proven in the formal sense. Proving it would almost certainly require resolving the P versus no problem or something equally deep. And that problem has resisted the efforts of the greatest mathematical minds for over half a century. This means that the entire edifice of quantum advantage rests on a foundation that is empirically overwhelming but formally unproven. We are extraordinarily confident that quantum computers can do things classical computers cannot, but we cannot write the proof on a blackboard. This is not a weakness of quantum computing. It is a reflection of how hard the underlying mathematical questions are. The same kind of uncertainty haunts classical complexity theory. We believe P does not equal no problem, but we cannot prove it either. The foundations of computational complexity are riddled with conjectures that everyone believes and no one can prove. So when someone tells you that a quantum computer has achieved supremacy, what they really mean is that a quantum device has performed a task that would be extraordinarily expensive for any known classical algorithm. They do not mean that a classical algorithm definitely cannot do it. They mean that no one has found a way yet. And the history of the field shows that classical algorithm designers are remarkably creative. Every quantum supremacy claim has been followed by a wave of classical improvements that narrow the gap. Does this mean quantum advantage is an illusion? No, absolutely not. It means that the frontier between classical and quantum computation is not a clean, bright line. It is a contested no man's land. Classical researchers are digging trenches on one side, quantum engineers are building machines on the other. And the territory between them is shrinking, not because classical methods are catching up in any absolute sense, but because both sides are advancing and the quantum side is advancing faster. This is the key point that most discussions miss. The classical improvements are real and they are impressive. Tensor network methods, approximate simulation algorithms, GPU accelerated sampling techniques, these have all pushed the boundary of classical simulation further than anyone expected a decade ago. But they are pushing against an exponential wall. They are finding clever paths through the foothills. They are not climbing the mountain. Every classical trick exploits some specific structure in the problem, some limited entanglement, some symmetry, some approximation that makes the computation tractable. When that structure is absent, when the quantum computation generates genuine, deep, complex entanglement across hundreds of qubits, no classical trick can help. The exponential wall reasserts itself with absolute authority. And this is precisely what fault-tolerant quantum computers will produce. NISQ devices operate in the contested zone. Their circuits are shallow, their qubit counts are modest, and their entanglement patterns are often structured enough for classical methods to exploit. That is why the supremacy claims have been debatable. But a fault-tolerant machine running deep circuits on hundreds of logical qubits will generate entanglement structures that no tensor network can compress, no approximate method can capture, and no GPU cluster can simulate. It will operate in a regime where the exponential scaling of Hilbert space is fully unleashed, and the classical foothills are 1,000 miles behind. This is what genuine quantum advantage looks like. Not a 3-minute sampling experiment on a contrived problem. Not a benchmark race between a quantum chip and a classical supercomputer where both sides are pushing the limits of their respective technologies. Real quantum advantage is the moment when a fault-tolerant quantum computer performs a computation, a useful computation, a simulation of a molecule, an optimization of a supply chain, a calculation in quantum field theory, that no classical machine can reproduce regardless of how much time, how much memory, or how clever an algorithm you throw at the problem. That moment has not arrived yet, but the trajectory toward it is now unmistakable. Let us be concrete about what that moment might look like. One of the most promising near-term applications of quantum computing is the simulation of quantum chemistry. The behavior of electrons in molecules is governed by the Schrödinger equation, and solving that equation exactly for molecules with more than a handful of atoms is exponentially expensive on a classical computer. Chemists have developed brilliant approximate methods, density functional theory, coupled cluster calculations, and others that work astonishingly well for many molecules. But there are systems where these approximations fail. Strongly correlated systems, transition metal catalysts, high-temperature superconductors, the active sites of enzymes. These systems have electronic structures so complex, so deeply entangled, that no classical approximation can capture them faithfully. A fault-tolerant quantum computer could simulate these systems directly. It could represent the electronic wave function in its full quantum glory, track the entanglement, capture the correlations, and produce results that no classical method can match. This would not be a supremacy demonstration. It would be a scientific discovery. It would be the moment when quantum computing stops proving it is fast and starts proving it is necessary. Another domain is materials science. The properties of quantum materials, superconductors, topological insulators, quantum magnets, are determined by the collective behavior of vast numbers of interacting quantum particles. Classical simulation of these systems is limited to small sizes or simplified models. A quantum computer could simulate larger, more realistic models and potentially predict new materials with exotic properties. The design of room temperature superconductors, one of the great white whales of condensed matter physics, might ultimately require quantum simulation to explore the vast space of possible material structures. Then there is quantum field theory, the mathematical framework that underlies particle physics, calculations in quantum chromodynamics, the theory of the strong nuclear force, are performed on classical computers using a technique called lattice gauge theory. These calculations are heroically difficult. They require the largest supercomputers on Earth, and they are limited to specific regimes. Certain quantities, like the real-time dynamics of quark-gluon plasma, are essentially impossible to calculate classically because of the sign problem. A quantum computer could, in principle, simulate these systems directly, opening a window into the behavior of matter under the most extreme conditions in the universe. These applications are years away. They require fault-tolerant machines with hundreds or thousands of logical qubits, which in turn require millions of physical qubits with current error correction overhead. But the roadmaps are being drawn, the engineering milestones are being hit, and the trajectory, the unmistakable, accelerating trajectory, points toward a crossover that is not a matter of if, but when. And when that crossover happens, the relationship between classical and quantum computation will change permanently. It will not be like the transition from vacuum tubes to transistors, where the new technology simply did the same thing faster. It will be like the invention of the telescope. Before the telescope, we could see the moon and the planets with our naked eyes. We could measure their positions. We could predict eclipses. But there was an entire universe of detail: craters, moons of Jupiter, rings of Saturn, galaxies, that was permanently invisible to us. The telescope did not just improve our vision, it revealed a category of reality that unaided eyes could never access. Quantum computers will do the same thing for computation. They will not just solve problems faster, they will solve problems that exist in a computational space that classical machines cannot enter at all. The molecules that are too entangled for classical chemistry. The materials whose quantum properties emerge from correlations too complex for classical simulation. The quantum field theories whose dynamics involve sign problems that classical methods cannot resolve. These are not faster versions of classical problems. They are new territory. They are the craters and the moons of Jupiter, invisible until you build the right instrument. But this analogy, powerful as it is, misses something. When Galileo pointed his telescope at Jupiter and saw 4 tiny points of light orbiting it, he could show anyone. He could invite a skeptic to look through the lens. The evidence was right there, visible to any pair of functioning eyes. The telescope extended human perception, but the output was still perceptible. You could see the moons, you could draw them, you could confirm them. A quantum computer is a telescope that points into a space you cannot see. Its internal operations unfold in a Hilbert space of unimaginable dimension. The computation is not a sequence of steps you can follow on a blackboard. It is a rotation of a vector through a space with more dimensions than atoms in the universe. The output, the answer that appears on the screen when the computation is complete, is the only thing you can see. The process that produced it is hidden behind the exponential wall. You see the destination. You cannot see the journey. This creates a situation that has no precedent in the history of science. With every previous instrument, from the microscope to the particle collider, we could in principle understand the chain of cause and effect that produced the observation. Photons bounced off the specimen and entered the lens. Protons collided and produced debris that hit the detector. The causal chain was classical, or at least classically describable. We could trace it. We could model it. We could simulate it on a classical computer, at least in principle. With a fault-tolerant quantum computer operating in the beyond classical regime, that chain breaks. The causal process inside the machine, the sequence of quantum gates acting on logical qubits, the entanglement building and spreading across the system, the interference patterns constructing the answer, all of this happens in a space that no classical system can model. You cannot trace it. You cannot simulate it. You cannot replay it on any classical machine. The internal process is classically opaque. The machine produces an answer, and the answer emerges from behind a curtain that no classical eye can lift. This is the crack that opens into the deepest problem of all, because if the process is hidden, if the internal computation cannot be classically reproduced, then how do you know the answer is right? You ran a quantum simulation of a complex molecule. The machine says the ground state energy is a specific number. You cannot check that number by running the same simulation on a classical computer, because the whole point is that the classical computer cannot do it. You cannot step through the quantum logic gate by gate, because measuring intermediate states would collapse the computation. You have a number on a screen and a machine that says, "Trust me." For the entire history of science, verification has been the bedrock of knowledge. You do the experiment, someone else repeats it. The results agree. That is how we know something is true. But what happens when the experiment cannot be repeated by any classical means? What happens when the only machine that can check a quantum computer's answer is another quantum computer? We have arrived at the edge of a cliff. The fog of hype is behind us. The landscape of real quantum advantage stretches out below, vast and strange and genuine. But the ground ahead is uncertain, because the next question is not about what quantum computers can do. It is about what we can know about what they have done. Let us sit with that question for a moment, because it is not a theoretical question. It is not a puzzle for philosophers to chew on over wine. It is a practical, immediate, engineering-level crisis that the quantum computing community is quietly grappling with right now, and it strikes at the very foundation of what we mean by knowledge. The entire scientific method, the engine that has driven human civilization from alchemy to antibiotics, from astrology to astrophysics, rests on a single principle: reproducibility. You perform an experiment. You record the result. Someone else, anywhere in the world, performs the same experiment. They get the same result. That agreement is what turns a measurement into a fact. It is what separates science from opinion. It is the bedrock. For classical computation, reproducibility is trivial. If a supercomputer calculates the trajectory of a spacecraft and produces a number, any other sufficiently powerful computer can run the same calculation and produce the same number. You can even check it by hand if you have enough patience and enough paper. The logic is transparent. Every step is deterministic. Every intermediate result can be inspected. You can pause the computation at any point, look at the state of the machine, verify that the logic is sound, and resume. Classical computation is an open book. Every page is legible. Quantum computation is a sealed vault. The reason is fundamental, not practical. It is not that we have not built good enough measurement equipment. It is not that the engineering is immature. It is that the laws of quantum mechanics forbid the kind of inspection that classical verification requires. When a quantum computer is in the middle of a computation, its qubits are in a complex, entangled superposition. The information is distributed across the entire system in a state that occupies an exponentially large Hilbert space. If you try to look at that state, if you try to measure the qubits to see what they are doing, the measurement collapses the superposition. The act of checking destroys the computation. It is as if opening the hood of your car caused the engine to vanish. You cannot peek. You cannot take a snapshot of the intermediate state. You cannot insert a debugger into the quantum logic and step through it instruction by instruction. The computation is a sealed process that begins with an input, evolves through a classically unimaginable space, and produces an output. The input and the output are classical. They are numbers you can read on a screen, but the journey between them is quantum, and that journey is permanently hidden. This is not just an inconvenience, it is a fundamental epistemological boundary, and it becomes a crisis the moment the quantum computer enters the beyond classical regime. As long as a quantum computer is solving problems that a classical machine can also solve, verification is straightforward. You run both machines, you compare answers. If they agree, you have confidence. This is exactly what researchers do today with NISQ devices. They run a quantum circuit, extract a result, and then simulate the same circuit on a classical computer to check. It is slow. It is expensive, but it is possible because the circuits are small enough to fit within the classical simulation boundary. But the entire point of building a fault-tolerant quantum computer is to leave that boundary behind. The entire point is to solve problems that classical machines cannot. And the moment you succeed, the moment the quantum computer produces an answer to a problem that no classical machine can solve, you lose your safety net. There is no classical oracle to consult. There is no second opinion available from the world of deterministic machines. The quantum computer hands you an answer, and you are standing alone with it. How do you know it is correct? This question has haunted the field since its inception, and over the decades, theorists have developed several strategies to address it. None of them are perfect. Each has limitations, but together, they sketch out the boundaries of what verification might look like in a post-classical world. The first and most comforting strategy applies to a special class of problems where checking the answer is dramatically easier than finding it. The textbook example is factoring. If a quantum computer uses Shor's algorithm to factor a large number, say a number with thousands of digits, the output is a pair of prime factors. Checking the answer is trivial. You multiply the two primes together. If you get the original number, the answer is correct. The computation took the quantum machine a polynomial amount of time. The verification takes a classical machine a fraction of a second. This is the dream scenario. The quantum computer does the hard work. The classical verifier just checks the receipt. But factoring is exceptional. Most problems of scientific interest do not have this convenient asymmetry between finding and checking. Consider quantum simulation, the application that Feynman dreamed about. You want to know the ground state energy of a complex molecule. The quantum computer runs a variational algorithm, explores the energy landscape, and returns a number. How do you check it? You cannot simply plug the number back into an equation and verify it, because the equation itself is what you could not solve classically. The answer is the output of an exponentially complex computation, and there is no shortcut for verification. You are in the position of a student who receives a number from a calculator and has no way to verify it except by using another calculator of equal power. The second strategy involves what theorists call interactive proofs. This is a protocol in which the quantum computer and a classical verifier engage in a dialogue. The verifier asks the quantum machine a series of carefully designed questions. The machine responds. Based on the pattern of responses, the verifier can determine with high probability whether the machine is performing the computation honestly. The key insight is that the verifier does not need to perform the computation itself. It just needs to ask the right questions. This sounds almost magical, and in a formal sense, it is one of the most beautiful results in theoretical computer science. In 2018, a landmark paper by Urmila Mahadev showed that a purely classical verifier can verify the output of a quantum computation, provided the quantum computer is unable to break certain cryptographic assumptions. The protocol works by forcing the quantum machine to commit to its internal state in a way that can be checked classically. If the machine tries to cheat, the inconsistency is caught. If it computes honestly, the verification succeeds. This was a breakthrough. It proved, in principle, that classical verification of quantum computation is possible. But there are caveats. The protocol is extremely expensive in terms of the overhead it imposes on the quantum computation. It requires the quantum machine to perform far more work than the original problem demands. It relies on cryptographic assumptions that, while widely believed to be secure, have not been proven secure. And it assumes that the quantum computer is a single, non-communicating entity that cannot collude with an outside party. In practice, implementing Mahadev's protocol on a real quantum computer is far beyond current engineering capabilities. It is a theoretical proof of possibility, not a practical tool. A third approach is called blind quantum computation. Imagine you do not have a quantum computer, but you want to use one owned by someone else, say a cloud service. You want to send your problem to the quantum server, have it compute the answer, and send it back. But you do not trust the server. Maybe you suspect it is cutting corners. Maybe you worry it is returning fabricated results. Blind quantum computation is a protocol that allows a classical client to delegate a quantum computation to an untrusted quantum server in such a way that the server cannot learn what problem it is solving, and the client can verify that the computation was performed correctly. Several versions of this protocol have been proposed and even experimentally demonstrated on small scales. They rely on the client having access to a very modest quantum device, sometimes as simple as a source of single photons. The client uses this minimal quantum capability to encrypt the computation and verify the output. Blind quantum computation is promising, but it too has limitations. It requires some quantum capability on the client side. It imposes significant communication overhead, and it has only been demonstrated for small, simple computations. Scaling it to the regime where verification is actually needed, where the quantum computer is operating far beyond classical reach, remains an open challenge. A fourth strategy, perhaps the most pragmatic, is cross-checking between quantum computers. If you have two independent quantum computers built by different teams using different hardware platforms, you can run the same computation on both and compare answers. If a superconducting machine and a trapped ion machine both return the same ground state energy for a molecule, your confidence increases. The errors in the two machines are different. The noise profiles are different. The likelihood that both machines make the same mistake in the same direction is low. This is the quantum analog of scientific reproducibility. You do not need a classical check. You need a quantum second opinion. This approach has real merit. It is practical. It does not require exotic protocols. It leverages the diversity of quantum hardware platforms. And as the field matures, with multiple companies and laboratories building fault-tolerant machines based on different technologies, cross-platform verification will become increasingly feasible. But it has a deep philosophical limitation. It tells you that two machines agree. It does not tell you that either of them is correct. If both machines share a common flaw, a subtle error in the implementation of a quantum algorithm, a systematic bias in the compilation of quantum circuits, they could agree on a wrong answer. Agreement increases confidence, but it is not the same as proof. There is also a more subtle approach rooted in the structure of quantum mechanics itself. Certain quantum computations produce outputs that carry internal signatures of correctness. For example, in quantum simulation, the output state might obey certain symmetries or conservation laws. If the quantum computer returns a state that violates energy conservation or breaks a known symmetry of the system, you know something went wrong, even without classically simulating the full computation. These consistency checks are valuable. They catch gross errors, but they are not comprehensive. A computation can satisfy every known symmetry and conservation law and still be wrong in ways that only a full classical simulation could detect. And a full classical simulation is precisely what we cannot do. So, where does this leave us? It leaves us in a position that is genuinely new in the history of human knowledge. We are approaching a regime where our most powerful computational tool produces results that we must accept on the basis of trust, not blind trust, not religious faith, but a structured, layered trust built from multiple sources. We trust the theory of quantum mechanics, which has been verified to extraordinary precision over the last century. We trust the engineering of the quantum hardware, which has been calibrated and tested at the physical qubit level. We trust the error correction protocols, which have been mathematically proven to work below the threshold. We trust the cross-checks between independent machines. We trust the internal consistency of the outputs. Each layer adds confidence, but none of them, individually or collectively, amount to the kind of ironclad verification that classical computation provides. This is not how science usually works. When the Large Hadron Collider detects a new particle, the detection itself is staggeringly complex. Millions of collision events, sophisticated pattern recognition, statistical analysis that would fill a library. But in principle, every step of the analysis can be replicated on a classical computer. The raw data is classical. The reconstruction algorithms are classical. The statistical tests are classical. The chain from observation to conclusion is classically transparent. A quantum computer operating in the beyond classical regime breaks this chain. We are approaching a regime where our most powerful computational tool produces results that we must accept on the basis of trust. The output appears, and the process that produced it recedes into a Hilbert space that no human and no classical machine can enter. Some physicists find this exhilarating. They see it as the natural next step in the long retreat of human intuition before the advance of formal mathematics. We gave up the intuitive picture of absolute space and time when Einstein arrived. We gave up the intuitive picture of deterministic particles when quantum mechanics arrived. Now we may have to give up the intuitive picture of transparent computation. We may have to accept that some computations are correct not because we can check them, but because the mathematics of quantum error correction guarantees them with overwhelming probability. Just as we accept that a bridge will hold not because we watch every atom in the steel, but because the mathematics of structural engineering guarantees it, others find it deeply troubling. And the concern is not merely practical, it is about the nature of understanding itself. The distinction between obtaining a correct answer and actually comprehending that answer is one of the oldest tensions in the philosophy of science. If a quantum computer produces the answer to a problem in quantum gravity, say a calculation relevant to the behavior of black holes or the structure of space-time, and no classical system can check that answer, then in what sense do we understand it? We have a number, we have a result, but we do not have comprehension. We cannot trace the logic, we cannot build the intuition, we cannot see why the answer is what it is. We can only see that it is. This distinction between having an answer and understanding an answer may seem philosophical, but it has real consequences for how science progresses. Scientific understanding is not just about collecting correct results. It is about building mental models, frameworks that allow human minds to make predictions, to see connections, to generate new hypotheses. When a physicist understands why the sky is blue, they do not just know that the answer involves Rayleigh scattering. They have a mental picture of photons bouncing off molecules. They can extend that picture to explain why sunsets are red. They can predict what the sky would look like on Mars. Understanding is generative. It produces new knowledge. A correct answer without understanding is a dead end. It tells you what, but not why. And science lives in the why. If quantum computers produce results that we cannot classically trace, we may find ourselves in possession of correct answers to deep questions, answers about the behavior of exotic materials, the dynamics of quantum fields, the structure of complex molecules, without any accompanying understanding. We will have the numbers. We will not have the narrative. We will have the destination. We will not have the map that led there. This is unprecedented. In every previous era of scientific discovery, the tool and the understanding evolved together. The telescope showed us the moons of Jupiter, and Newtonian mechanics explained their orbits. The particle collider produced new particles, and quantum field theory explained their properties. The instrument and the theory were partners. Each informed the other. Each made the other more powerful. But a fault-tolerant quantum computer operating in the beyond classical regime might decouple this partnership. The instrument could leap ahead of the theory. It could produce results that our theoretical frameworks cannot explain, not because the theories are wrong, but because the theories require classical verification that is no longer possible. We would be in the strange position of having a machine that knows more than we do. Not in the science fiction sense of artificial intelligence. The quantum computer is not thinking. It is not conscious. It is not making decisions. It is executing a quantum circuit. But the execution takes place in a space that our minds and our classical tools cannot follow. The machine is not smarter than us. It is operating in a dimension we cannot see. There is an analogy that might help. Imagine a brilliant mathematician who can see in 4 spatial dimensions. She can visualize 4-dimensional objects the way you visualize cubes and spheres. She produces theorems about 4-dimensional geometry that are correct, proven, and rigorous. You can read the proofs. You can follow the logic step by step. But you cannot see what she sees. You cannot visualize the objects she is describing. You trust the proofs because the axioms are sound and each step follows from the previous one. But your understanding is formal, not intuitive. You know the theorems are true. You do not feel why they are true. A quantum computer operating in a Hilbert space of 1,000,000 dimensions is like this mathematician. Its outputs are correct. The axioms of quantum mechanics are sound. Each gate in the circuit follows logically from the previous one. But the space in which the computation unfolds is so far beyond human visualization, so far beyond classical simulation, that our understanding of the result is purely formal. We trust it because we trust the axioms. We do not grasp it because we cannot see the space. And here is where the verification crisis meets something deeper, something that goes beyond engineering and enters the territory of philosophy. Because the verification problem is not just about checking answers. It is about the relationship between humanity and its tools. For the entire history of civilization, our tools have been extensions of our bodies and our minds. The hammer extends the fist, the telescope extends the eye, the computer extends the brain. But in every case, the tool operated in a domain that we could, in principle, access. We could see what the telescope saw. We could follow what the computer calculated. The tool amplified our capabilities, but it did not exceed our comprehension. A fault-tolerant quantum computer is the first tool in human history that will operate in a domain we cannot access. Not in practice. In principle, the Hilbert space of a few hundred logical qubits is not a space we have not yet explored. It is a space we cannot explore, even with unlimited classical resources. It is not a mountain we have not yet climbed. It is a mountain that exists in a dimension perpendicular to every dimension we can perceive. The tool is no longer an extension of the human mind. It is a departure from it. It computes in a realm that the human mind and every classical model of the human mind cannot follow. This does not mean the results are untrustworthy. The mathematics of quantum error correction is rigorous. The theory of quantum computation is well-founded. The layers of verification, interactive proofs, cross-platform checks, consistency tests, symmetry constraints provide real confidence. But confidence is not the same as comprehension. We may reach a point where we have machines that reliably produce correct answers to questions we cannot independently verify, answers that emerge from processes we cannot classically model, computed in spaces we cannot classically describe. We will trust the answers the way we trust the laws of quantum mechanics themselves, because every test we can perform is consistent, because the mathematical framework is self-consistent, because the track record is flawless. But we will not understand the answers the way we understand classical calculations. We will not be able to open the book and read every page. This is the verification crisis, not a crisis of correctness. The machines will almost certainly be correct, within the bounds guaranteed by error correction. It is a crisis of transparency, a crisis of the human capacity to follow its own creations into the dark. We are building instruments that will journey into a computational space beyond the horizon of classical knowledge, and they will return with treasures we cannot independently appraise. We will hold those treasures in our hands. We will use them to build new technologies, to design new materials, to understand new physics. But we will hold them with a specific kind of faith, a faith in the formalism, a faith in the mathematics, a faith in the machine. And that faith will be well-founded. It will be built on the most successful physical theory in history. It will be supported by layers of redundancy and cross-verification. It will be earned, not assumed, but it will still be faith, because at the end of the day, the only machine that can fully verify what a quantum computer has done is another quantum computer. And that is a circle from which classical knowledge cannot escape. We are almost at the edge now. The wall of classical simulation, the rise of error correction, the true meaning of quantum advantage, the crisis of verification. Each of these threads is converging on a single point, a point that is not just technological but civilizational. A boundary that, once crossed, restructures the relationship between human intelligence and the physical universe. It is time to name that boundary. It is time to look at what lies on the other side, and it is time to understand why, once we step across it, we can never come back. Let us go back to where we started, to the phrase that has been hovering over this entire journey like a shadow, the point of no return. We have been building toward it. We have laid the foundation stone by stone. The exponential wall of classical simulation, the phase transition of error correction, the contested frontier of quantum advantage, the crisis of verification. Each of these was a step on a staircase. And now we are standing at the top, looking out over a landscape that no generation before us has ever seen. But before we step forward, we need to understand exactly what this threshold is, because it is not what most people think. It is not a date on a calendar. It is not a press conference where a CEO holds up a chip and declares victory. It is not the moment a quantum computer factors a large number or simulates a specific molecule. Those are milestones. They are important, but they are not the threshold. The threshold is something more fundamental, more permanent, more unsettling. The point of no return is the moment when scalable, fault-tolerant quantum systems become too complex to be fully modeled by any classical system that could exist within the physical universe. It is not a moment of engineering triumph. It is a structural boundary in the architecture of knowledge itself. It is the line beyond which our tools permanently exceed our ability to simulate them, to trace their logic, to independently verify their internal processes using any classical means. And unlike every other boundary humanity has crossed, this one does not lead to a new territory that can eventually be mapped with classical tools. It leads to a territory that is, by mathematical proof, classically unmappable. Forever. Let us be precise about what forever means here. When we split the atom, we entered a regime that was dangerous but classically describable. Nuclear reactions can be modeled on classical computers. The calculations are difficult, but they are polynomial. A big enough supercomputer can handle them. When we discovered quantum mechanics itself, we entered a regime that was deeply counterintuitive, but still, for small systems, classically tractable. When we split the atom, we entered a regime that was strange but classically simulable. Nuclear reactions can be modeled on classical computers. The calculations are difficult, but they are polynomial. A big enough supercomputer can handle them. When we discovered quantum mechanics itself, we entered a regime that was deeply counterintuitive, but still, for small systems, classically tractable. A hydrogen atom can be solved exactly with pencil and paper. A helium atom can be approximated with great precision on a laptop. But a fault-tolerant quantum computer with a few hundred logical qubits operates in a Hilbert space whose dimensionality, as we saw, outstrips any physical quantity in the known universe. And, as we also saw, this is not a gap that more hardware can close. No engineering effort, no algorithmic insight, no future breakthrough in classical chip design changes the arithmetic. The classical simulation is not merely impractical, it is physically impossible. Not impossible given current technology, impossible given the laws of physics as we understand them. Not impossible given current technology, impossible given the laws of physics as we understand them. The universe does not contain enough stuff to classically represent what the quantum computer is doing. This is the key distinction. Every previous technological threshold was a barrier of degree. We needed more speed, more power, more precision, but the barrier was made of the same material as the solution. Classical physics posed the problem, and classical physics provided the tools to solve it. The quantum computational threshold is a barrier of kind. The problem is posed in a mathematical language, exponential Hilbert space, that classical tools cannot speak. The barrier is not made of engineering challenges, it is made of mathematics. And mathematics does not erode with time. It does not yield to funding or ingenuity. 2 to the power of 300 will always be larger than 10 to the power of 80. The wall is permanent. Now let us trace the consequences of this permanence, because they ripple outward in ways that touch every corner of human knowledge. The first consequence is the end of universal classical simulation. For the entire history of physics, we have operated under an implicit assumption. The assumption that any physical process can, in principle, be simulated on a classical computer. This assumption was never proven. It was never even formally stated as a law. It was just a background belief, a comfort blanket that let physicists sleep at night. If the universe does something strange, We assumed we could always build a classical model that reproduces the behavior. Maybe the model would be slow. Maybe it would require enormous resources, but it would be possible. This assumption is about to be violated when a fault-tolerant quantum computer performs a computation using 300 logical qubits. The internal process involves a quantum state in a Hilbert space of 2 to the power of 300 dimensions. No classical model can represent this state. No classical computer can track its evolution. The physical process happening inside the quantum chip is a real physical event, governed by real physical laws, producing real physical outcomes, and it cannot be classically simulated, not because we are lazy, not because we lack resources, because the classical description of the process requires more information than the physical universe can contain. This means that for the first time, humanity will be operating a physical system whose behavior is beyond classical description. The machine will be real. You will be able to touch it. You will be able to see it humming in its cryostat or its vacuum chamber. The inputs will be classical. The outputs will be classical. But the internal process, the thing the machine is actually doing, will exist in a realm that classical physics cannot reach. We will have built a piece of reality that our classical understanding of reality cannot encompass. Think about what that means for the concept of physical law. We write physical laws as equations. Those equations are classical objects. They live on paper or on screens. They are processed by classical minds and classical computers. Our entire framework for understanding nature is classical at its root. Quantum mechanics is formulated in the language of linear algebra and differential equations, all of which are classical mathematical tools. We use classical logic to derive quantum predictions. We use classical computers to solve quantum equations. The interpretive layer, the layer where humans understand what nature is doing, has always been classical. But the quantum computer operates in a space that this classical interpretive layer cannot model. The machine speaks quantum natively. It does not translate quantum mechanics into classical language. It does not approximate. It does not compress. It operates in the full, unexpurgated, exponentially vast Hilbert space, and we, standing outside, can only receive what it delivers. We see the output arrive on a classical screen. We see a number, a measurement, a prediction, but the process that produced it unfolded in a space we have no classical window into. The machine went somewhere we cannot follow, and it came back with something in its hands. The second consequence is the emergence of computational irreversibility. In every previous era, knowledge has been bidirectional. We build a tool, we understand the tool, we use the tool to discover something. We understand the discovery. The act of knowing and the act of doing have always been linked. You could always, in principle, reverse engineer the process. You could always trace backward from the result to the method. You could always ask not just what, but how, and get an answer that a human mind could follow. Quantum computation beyond the classical threshold breaks this link. The computation goes in one direction, from input to output, through a process that cannot be classically reversed. You cannot start from the output and reconstruct the intermediate quantum states. You cannot decompose the computation into classically meaningful steps. The information about how the answer was produced is not hidden. It is destroyed, not by any act of erasure, but by the structure of quantum measurement itself. The intermediate states exist in a superposition that is projected, collapsed, flattened into a classical output. The richness of the quantum process is reduced to a single classical shadow, and from that shadow, the original object cannot be reconstructed. This is computational irreversibility. And it is not a limitation of our current tools. It is a theorem. Mathematically, The amount of classical information required to fully describe the intermediate states of a quantum computation grows exponentially with the number of qubits. No future classical technology, no matter how advanced, can store or process that information. The irreversibility is baked into the physics. It is permanent. The third consequence, and perhaps the most profound, is a permanent shift in the boundary between the knowable and the unknowable. Throughout the history of science, that boundary has moved. Things that were once unknowable, the composition of stars, the age of the universe, the structure of DNA, became knowable as our instruments improved. The story of science is, in many ways, the story of the knowable expanding at the expense of the unknowable. Every century, the circle of light grows and the darkness retreats. But the quantum computational threshold introduces a new kind of unknowable, not the unknowable of ignorance, which yields to better tools, but the unknowable of principle, which persists regardless of tools. The internal process of a beyond classical quantum computation is not unknowable because we have not yet figured out how to observe it. It is unknowable because the observation would require classical resources that exceed the physical limits of the universe. This is a hard wall. It does not retreat. The circle of classical light has reached its maximum diameter. Beyond it, there is a darkness that no classical lantern can penetrate. This does not mean we are helpless. We have the quantum computer itself. It can navigate that darkness. It can return with answers. But we, the classical minds holding the lantern, cannot follow it in. We cannot see what it sees. We cannot map where it has been. We must trust its report the way an explorer trusts a scout who returns from a land the explorer can never visit. The scout brings back specimens, measurements, descriptions. The explorer can test them, cross-reference them, check them for internal consistency. But the explorer can never go there and see for herself. This creates a new epistemological category. Call it quantum-mediated knowledge. It is knowledge obtained through a process that is classically opaque. The knowledge itself is classical. It is a number, a measurement, a prediction that can be written on paper and discussed in plain language. But the path to that knowledge passes through a quantum space that defies classical description. The knowledge is real. It is reliable, backed by the full weight of quantum error correction and the mathematical structure of quantum mechanics. But it is derived from a process that no classical mind can fully comprehend. We have never had knowledge like this before. Every piece of scientific knowledge in human history was derived through a chain of reasoning or observation that could, in principle, be followed by a sufficiently patient and intelligent classical mind. A human could, in principle, trace the logic from axiom to theorem. A classical computer could, in principle, replicate the computation from input to output. Quantum-mediated knowledge breaks this chain. It introduces a gap in the inferential pathway, a quantum leap in the literal sense, where the reasoning passes through a space that classical logic cannot traverse. Now, some will argue that this is not fundamentally different from other situations in science, where we trust instruments we do not fully understand. We trust MRI machines without understanding every detail of nuclear magnetic resonance. We trust GPS satellites without understanding general relativity. We trust pharmaceutical drugs without understanding every biochemical pathway they affect. Trust in instruments is not new, but there is a crucial difference. In all of those cases, the instrument's operation can, in principle, be classically modeled. We can simulate the physics of an MRI machine on a classical computer. We can derive the relativistic corrections for GPS from Einstein's equations using pencil and paper. The trust is practical, a shortcut to avoid redoing calculations we know how to do. It is not fundamental. We choose not to verify. With a beyond classical quantum computer, we cannot. The distinction is not between choosing not to verify and being unable to verify. It is between optional trust and necessary trust. For the first time, we will rely on a tool whose correctness we are structurally incapable of independently confirming through any classical means. This is a new relationship between humanity and its instruments, and it is permanent. No future classical technology will change it. The gap is mathematical, not technological. What does this permanence mean for the long arc of civilization? Let us step back and look at the biggest picture we can. Every great revolution in science has been, at its core, a revolution in the relationship between the human mind and the physical world. Copernicus shattered the illusion that we occupy the center of the cosmos. Darwin shattered the illusion that we occupy a special place in the tree of life. Einstein shattered the illusion that space and time are absolute. Quantum mechanics shattered the illusion that reality is deterministic and objective. Each of these revolutions took something away. Each one diminished the human ego. Each one forced us to accept that the universe is less anthropocentric, less intuitive, less comfortable than we imagined. The quantum computational revolution follows this pattern, but it goes further. The previous revolutions changed what we know about the universe. They revealed new facts. The Earth orbits the Sun. Species evolve. Time dilates. Particles exist in superpositions. These facts were shocking, but they were comprehensible. We could learn them. We could teach them. We could build intuitions around them, however imperfect. The quantum computational revolution does not just change what we know, it changes what we can know. It draws a line around the capabilities of classical reasoning itself. It says to the human mind, you can go this far and no further. Not because the universe is hiding, but because the universe computes in a language your classical architecture cannot fully decode. This is not a depressing conclusion, it is a humbling one. There is a difference. Depression comes from the belief that something valuable has been lost. Humility comes from the recognition that something was never ours to begin with. The ability to classically simulate every physical process in the universe was never a guaranteed feature of reality. It was an assumption, a hope, a background radiation of scientific optimism. The quantum computational threshold reveals that this assumption was wrong. The universe is richer than classical simulation can capture. It always has been. We are just now building machines that make this richness operational, and in a strange way, this is cause for awe rather than despair. Consider what it means that the mathematics we have been describing is not speculative. It is the operating system of everything that exists. Every chemical bond, every beam of light, every magnetic field is a quantum process unfolding in a Hilbert space that classical description cannot capture. This has always been the case. What is new is not the quantum computation. What is new is that we are building machines that can participate in it deliberately, steering through those impossible dimensions and bringing back answers. The quantum computer is not introducing something alien into the world. It is our first engineered point of contact with the computational depth that was always there, running beneath the classical surface of things. This is the real significance of the point of no return. It is not that we are building machines that are too powerful for us to control. This is not a story about artificial intelligence or runaway technology. The quantum computer is not thinking. It is not conscious. It is not making choices. It is a precisely engineered physical system executing a precisely designed quantum circuit. It is a tool, but it is a tool that operates in a domain that transcends classical description. And that makes it the first tool in the history of intelligent life, as far as we know, that breaches the boundary between the classically knowable and the classically unknowable. We are not losing control. We are gaining access. access to a level of physical reality that was always there, always operating, always governing the behavior of matter and energy, but that our classical instruments and classical minds could never directly reach. The quantum computer is a bridge. It connects the classical world we inhabit, the world of definite measurements and readable screens, to the quantum world that underlies it, the world of superpositions and entanglements and Hilbert spaces that stretch beyond imagination. But bridges go both ways. And the knowledge that comes back across this bridge will transform every field it touches. Materials science will gain the ability to simulate quantum systems that are currently intractable, potentially unlocking new superconductors, new catalysts, new energy technologies. Drug discovery will gain the ability to model molecular interactions with quantum precision, potentially accelerating the development of therapies for diseases that have resisted classical computational approaches. Fundamental physics will gain a laboratory for testing ideas about quantum gravity, quantum field theory, and the structure of space-time that are currently beyond experimental reach. Each of these applications will produce knowledge that could not have been obtained by any classical means, and each will move humanity deeper into the post-classical era, an era where our most powerful knowledge is quantum-mediated, derived from processes we trust but cannot classically trace. There is a final thought that deserves to be spoken aloud, because it is the thought that sits beneath all the others, like bedrock. We are the universe's way of knowing itself. That is not a mystical claim. It is a straightforward observation. We are made of atoms. Those atoms were forged in stars. Those stars were born from clouds of gas that condensed under gravity from the primordial plasma of the Big Bang. We are the cosmos, arranged into a configuration that can ask questions about its own nature. Every telescope, every microscope, every particle collider has been an extension of this self-inquiry. The universe examining itself through instruments made of itself. The quantum computer is the most profound instrument in this lineage, because it does not just examine the universe from the outside, the way a telescope examines a distant star. It operates inside the quantum fabric of the universe. It participates in the same quantum computation that governs every particle, every field, every force. When a quantum computer manipulates qubits in superposition and entanglement, it is not representing nature from the outside. It is participating in the same physical processes that govern stars and atoms and everything in between. It is an instrument made of the same quantum fabric it explores. And this is what makes it different from every scientific instrument that came before. And this is why crossing the threshold is a point of no return. Once we have machines that operate natively in the quantum computational space, once we have tools that navigate Hilbert spaces beyond classical description, we cannot go back to a worldview where classical simulation is sufficient. We cannot pretend that the classical picture is complete. We have seen behind the curtain. We have touched the machinery, and the machinery is vaster, deeper, and stranger than anything our classical intuitions prepared us for. The point of no return is not the moment the machine turns on. It is the moment we realize that the machine is showing us a truth about the universe that we can never unsee. The truth that physical reality computes in a space that dwarfs our ability to describe it. The truth that our classical models, for all their power and beauty, are projections, shadows, compressed approximations of a quantum reality that operates on a scale that makes the observable universe look small. The truth that we have been living inside this quantum computation our entire lives, and only now, only with these machines, are we beginning to see where we really are. This is not the end of understanding, it is the beginning of a new kind of understanding, an understanding that is partially classical and partially quantum mediated. An understanding that trusts the formalism of quantum mechanics to deliver correct answers from spaces our minds cannot visit. An understanding that accepts the limits of classical reasoning not as a defeat, but as a doorway. Because on the other side of that doorway, The universe is richer than we ever imagined, and the machines we are building are the first eyes capable of seeing it. We will cross the threshold. The engineering is too far advanced, the trajectories too clear, the mathematical foundations too solid for the crossing to be prevented. And when we cross it, the relationship between humanity and physical law will change in a way that cannot be reversed. We will become a species that possesses tools beyond its own classical comprehension. Not because we failed, but because we succeeded, because we built machines that speak the native language of the universe. And in doing so, we will learn that the universe has been speaking all along. We were just too classical to hear it. The machines are almost ready. The qubits are stabilizing. The error codes are holding. The Hilbert space is waiting. And on the other side of the threshold, the universe is vast.